Hi, welcome back, Dr. Nordin and everyone. My name is Aizzudin Azeem bin Syazlan. My matrix number is 208144, and I'm going to continue my presentation on part 2, the topic of dimensional analysis and modeling for the subject EMM 3305 fluid mechanics. So let's look into dimensions. So what is dimensions? All right, dimensions are a measurable extent of some base quantities. For examples, we have length, we have time, and we have mass. So units are labels for different dimensions and combination of dimensions. So the labels for different dimensions means that length, we have a unit of meter, and for time, we use the unit of second, and mass is the unit of a kilogram. And combination of dimensions, which means like force, for example, force is equal to mass times acceleration. So force, we use the unit as Newton, which is the combination of kilogram times meter per second square. Now, this is the example of dimensions with its units and symbols. We have length, mass, time, electric current, luminous intensity, temperature, and amount of substance. Next, what is dimensional homogeneity? Dimensional homogeneity is the concept where the dimensions of variables on both sides of equations are the same. For examples, we have here length equals to length over time times with time. So we have length, for example, we have length in meter equals to length here also in meter divided by second. So this is meter per second times with second. So we can cancel the time. So we will get meter on the right side and the left side is also meter. So this equation satisfies the dimensional homogeneity. An equation could be dimensionally homogeneous but invalid if the equation is not fully balanced. For example, let's say we have 2m equals to m. So even if we cancel each other for m, we will get 2 equals to 1. So mathematically that is wrong. So our equation is invalid, even though it is dimensionally homogeneous. Now, let's look into the further examples of dimensional homogeneity. So dimensional homogeneity. So the first one, we have 10 meter equals to 7 meter plus 3 meter. So in this example, the dimensional homogeneity is achieved because in both sides we have meter, and the equation is also valid because 7 plus 3 is equals to 10. For the next one, we have 6 newtons equals to 2 kilogram times 3 meter per second square. This is also valid because newton is actually equals to kilogram times meter per second square. But for the third one, this is a fluid mechanics equation. So we have here on the left side is pressure, which the unit is Pascal, or the SI unit is kilogram per meter second square, equals to density, which is in kilogram per centimeter cube. We have here is G over GC, where G, we have the dimension, the gravitational acceleration, we have the dimensions of length over time square divided by mass length over time square divided by force. So if you cancel each of this, we will get the dimension of force over mass. We will have force over mass here. So with times with h, which is distance, we have length, which is meter. When we times all of this, we will get kilogram per meter second square, which is the same on both sides. And we can also express it as Pascal. So this is also an example of dimensional homogeneity. Next. So dimensional analysis. The analysis of the relationships between different physical quantities by identifying their base quantities and units of measure and tracking these dimensions as calculations or comparisons are performed. So that is what the meaning of dimensional analysis. And dimensional analysis, we use the rule of algebra and it must obey the dimensional homogeneity concept. If they are not dimensionally homogeneity, we cannot the analysis will be wrong. So next one, this is the example of an analysis, dimensional analysis. As we can see here, if you want to convert kilometer per hour to miles per minute, we need to convert it. So we know that 1 mile is equal to 1.60934 kilometers. So we can cancel kilometer here, and also 1 hour equals 60 minutes. So we can cancel the hour here, then we will get miles per minute. But let's say if these questions ask us to convert kilometer per hour to miles per Kelvin, for example, then we cannot do the analysis. The analysis will be wrong because it does not satisfy the dimensional homogeneity because there is no temperature here, but here we will have temperature, so it's wrong. The next one is dimensional similarity. So what is the dimensional similarity? So there are actually three types of dimensional similarity. The first one is geometric similarity. The model must be the same shape as the prototype, but may be scaled by some constant scale factor. The second one is kinematic similarity, which means that the velocity at any point in the model flow must be proportional. And for the third one, dynamic similarity, when all forces in the model flow scale by a constant factor to corresponding forces in the prototype flow. So in general flow field, complete similarity between a model and a prototype is achieved when the geometric, kinematic, and dynamic similarity is there. So let's look into Buckingham pi theorem. What is a Buckingham pi theorem? So the Buckingham pi theorem states that an equation involving n number of physical variables which are expressible in terms of k independent fundamental physical quantities can be expressed in terms of p equals to n minus k dimensionless parameters. So let's look into the method of repeating variables. So this is actually what the Buckingham pi theorem teach us. So the first one is to list the parameters in the problem and count their total number, and list the primary dimensions of each of the n parameters, set the reduction j as the number of primary dimensions. We calculate the k, the expected number of, this is the Buckingham Pi's theorem, Buckingham Pi, and k equals to n minus j. We choose j repeating parameters, construct the k pi's and manipulate as necessary, write the final function, and check your algebra. So let's look into example. So the example, we have a question here. Obtain an expression in non-dimensional form for the pressure gradient in a horizontal pipe of circular cross-section. Show how this relates to the familiar expression for frictional head loss. So for the first, now let's look into the solutions of this problem. So the first one, we need to identify the relevant variables. So we have dP over dx, the change of pressure over length. We have the rho, density, volume, V, the diameter, D, the pipe constant is K, and mu, the viscosity. So step 2 is to write down dimensions. So for dP dx, we have force times area over length. So, force divided by area over length. Y is MLT, M is basically mass, L is length, and T is time. So we have kilogram, meter, and second. So for dP dx, we have ml to the power of -2 times t to the power of -2. And for rho, we have ml to the power of -3. For v, we have L times t to the power of -1. D, we have L. K, as we also have L. And for mu, we have ml to the power of -1 times t to the power of -1. So step 3 is to establish the number of independent dimensions and non-dimensional groups. So the relevant variables, say that we have listed down here, we have 6 relevant variables. That's why n is equals to 6. 1, 2, 3, 4, 5, 6. And for the next one is we have to know the number of independent dimensions. So we only have 3 dimensions here, which is mass, length, and time. So our m is equals to 3. So so for the non-dimensional groups, or the pi's, we will have 3. So n minus m, 6 minus 3, we will get 3. So choose M3 dimensionally independent scaling variables. For example, we have geometric D, kinematic time dependent V, dynamic over mass dependent rho. Now we need to create pi's by non-dimensionalizing the remaining variables. So since we got here a number of non-dimensional, we have 3, so we need to have 3 pi's. So for the first one, we will construct pi 1 equals to dP over dx times d times v times p, or we will put the power of d, v, and p as a, b, c. Because we need to make the equation achieve the homogeneity dimensions. So the same as the pi 2, we will have k s over d, and the pi 3 we will have mu times d times v times p. For the second one, we do not have to put a, b, c because we know k is L and d is also L, so the homogeneity is achieved here. But for 1 and 2, we need to put a, b, c, and we assume that the pi here is is 1. The SI unit. So that means we have m to the power of 0, L to the power of 0, t to the power of 0, the same as here. So now we need only to solve the ABC. We have to solve the ABC on each of these problems, there we will know the power of each dimensions. So far as after we have do the calculations, we can move on to step 6 to set out our non-dimensional relationship. So in this problem, we'll set out our pi1 equals to f times with f, pi2, and pi3. So we will have d dp dx over p v squared times f, k over d, and mu over rho v d. So step 7 is to rearrange for convenience. So for example, for the mu over rho vd, we can just replace it with Reynolds number. And also for the for the dp dx, we can replace it with gh. And it will become, for this part, it will become to GHD over LV square. So that is how we use the Buckingham Pi's theorem to determine our dimension. So let's look into dimensionless quantity. Dimensionless quantity is a quantity to which no physical dimension is assigned. So we can put the SI unit as 1. For example, we have Reynolds number, and also we have Froude number. And for Reynolds number, it's really important of all types of fluid dynamics problem. And we use it as to measure of the ratio of the inertia force to the viscous force. And for Froude number, it is important in problems involving flows with free surfaces. So for both of these number, we do not have unit. They only have the number, but they do not have the unit. That's why it is called dimensionless. So thank you. That is all for this part.